Right now, 3 astronomical units from the Sun. Something impossible is happening. A comet is spewing water vapor into space, 40 kilograms every second. That might not sound impossible to you yet, but here's the thing. At that distance, water ice shouldn't be doing anything at all. It should be frozen solid, locked in place, completely dormant. And yet, this comet is producing water like a cosmic fire hose. This is 3I Atlas, the third confirmed interstellar object ever detected. And it's not just breaking the rules, it's rewriting them. This object is ancient, 7 to 10 billion years old. That's older than our sun, older than Earth, older than everything you've ever known. It formed in another star system, orbited another sun, and has been wandering the galaxy for eons. And now, for just a brief moment in cosmic time, it's passing through our neighborhood. We have one chance to study it, one chance to learn what secrets it carries from the ancient universe. This is 3I Atlas, and this is its story. July 1st, 2025. The Atlas telescope system in Chile was doing what it does every clear night, scanning the sky for asteroids that might pose a threat to Earth. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. It's part of a global network designed to spot dangerous space rocks before they get too close. 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa. They work in coordination, capturing the same patches of sky multiple times per night, looking for anything that moves. On this particular night, the Chilean telescope caught something, a faint dot of light that hadn't been there before. Not unusual. ATLAS finds objects all the time. The initial assumption was simple, probably just another comet from our solar system's distant reaches. Log it, track it, move on. But as observations continued over the following days, something became clear. This wasn't a normal comet. The trajectory was wrong. When astronomers calculated its orbit, they found something startling. The path was hyperbolic. Not elliptical, hyperbolic. That single word changes everything. An elliptical orbit means an object is bound to the sun, cycling around it in a closed loop, part of our solar system family. A hyperbolic orbit means the object is just passing through. It came from somewhere else. It's heading somewhere else. It will never return. This was an interstellar visitor. The object was designated C/2025L1, Atlas, but everyone just calls it 3I Atlas. The 3I means third interstellar object. The first was Oumuamua in 2017. The second was Comet Borisov in 2019. And now, in 2025, we have our third confirmed visitor from beyond our solar system. Let me be clear about what interstellar really means. This object didn't form around our sun. It formed around a different star, light years away. At some point in its history, gravitational interactions ejected it from its home system. It was cast out into the void between stars, and it's been traveling through that void for billions of years. The distances involved are almost incomprehensible. The nearest star system to us is over 4 light years away. That's 40 trillion kilometers. 3I Atlas has been drifting through that kind of darkness for longer than our planet has existed. And now it's here, passing through, a messenger from another world. Now, I know what some of you are thinking. Interstellar object, anomalous behavior. Is it aliens? Let me address that right now. No, it's not aliens. But what it actually is might be even more fascinating than any science fiction. Because this isn't some manufactured probe. This is a natural object carrying a chemical fingerprint from another star system. It's a sample, delivered to us by chance, from a place we could never visit. It's a time capsule from the ancient galaxy. And that's worth paying attention to. So, what is this thing? Let's talk size first. Based on observations, the nucleus of 3I Atlas is estimated to be between 2 and 6 kilometers across. Think of a mountain, not a small hill. A proper mountain range compressed into a ball of ice and rock. The mass is approximately 30 billion tons. To put that in perspective, that's roughly the mass of 75,000 fully loaded aircraft carriers, or the Great Pyramid of Giza multiplied by 20,000. This is not a pebble. This is a massive chunk of ancient material, and it's moving fast. Currently traveling at around 210,000 kilometers per hour relative to the Sun. That's nearly 60 kilometers every second. At that speed, you could travel from New York to Los Angeles in under a minute. The kinetic energy alone is staggering. If this thing were to hit a planet, the result would be catastrophic on a scale that would make the dinosaur extinction event look modest. But it's not going to hit anything. Its trajectory is taking it through the solar system on a path that won't bring it close to any major planets. It's just passing through, untouched and untouchable. Now, here's where things get interesting. Under normal circumstances, comets are predictable. We know how they behave. When a comet from our solar system approaches the Sun, it starts to heat up. At around 3 astronomical units, about 3 times the distance from Earth to the Sun, water ice begins to sublimate. It transitions directly from solid to gas without becoming liquid. This creates the familiar comet tail, the coma of gas and dust that makes comets so spectacular to observe. But here's the key detail. That activity is driven by sunlight. The sun's radiation warms the surface of the comet, and the ice responds by vaporizing. The closer the comet gets to the sun, the more active it becomes. This is standard comet physics. We've observed it hundreds of times. 3I Atlas should follow the same rules, except it doesn't. In October of 2025, NASA's Neil Gehrels Swift Observatory, a space telescope designed to detect gamma-ray bursts and other transient cosmic phenomena, turned its attention to 3I Atlas. Swift has ultraviolet detectors that are particularly good at spotting the hydroxyl signature of water vapor. Hydroxyl is what you get when water molecules break apart under ultraviolet light. It's a telltale sign of active water production. When Swift observed 3I Atlas, it detected a strong hydroxyl signal. The comet was producing water, a lot of water, approximately 40 kilograms per second. 40 kilograms per second is not a trivial amount. That's equivalent to filling a bathtub every few seconds. Or imagine a garden hose the size of a bus, constantly spraying vapor into space. Over the course of a day, that's nearly 3.5 million kilograms of water. Over 1 million kilograms per day. And this had been going on for months. Now here's the problem. When Swift made these observations, 3I Atlas was at a distance of roughly 3 astronomical units from the Sun. At that distance, the sunlight is relatively weak. Only about 11% as intense as it is at Earth's orbit. At that level of solar radiation, water ice should barely be active. Most comets at that distance produce only minimal amounts of gas, if any at all. And yet, 3I Atlas was producing 40 kilograms of water every single second. Scientists were baffled. Dr. Dennis Bodowitz, an astronomer at Auburn University and one of the lead researchers studying 3I Atlas, stated publicly, "We did not expect to see this level of water production at such a great distance. This challenges our understanding of how comets activate." So the central question became, how is this possible? What's powering this water production? The sunlight isn't strong enough. So what's going on? Several theories emerged almost immediately. One possibility, maybe the comet isn't producing water vapor directly from surface ice. Maybe it's ejecting ice grains, tiny particles of solid water ice, which then sublimate in space after being released. This could explain the high production rate. Instead of the surface slowly vaporizing, chunks of ice are being thrown off, creating a much larger active area. But that raises another question. What's ejecting the ice grains? On normal comets, carbon monoxide and carbon dioxide can provide the energy. These molecules sublimate at much colder temperatures than water ice. As they vaporize beneath the surface, they can create pressure that cracks the surface and ejects material. Maybe 3I Atlas has a lot of carbon monoxide or carbon dioxide driving this process. That was the leading hypothesis. But to test it, scientists needed more data. They needed to know what this comet is actually made of. And that's where the real detective work began. To understand what a comet is made of, astronomers use a technique called spectroscopy. It's essentially cosmic detective work using light. When molecules in a comet's coma are excited by sunlight, they emit light at very specific wavelengths. Different molecules produce different patterns, like fingerprints. By analyzing the light coming from a comet, we can identify what chemicals are present. But there's a challenge. 3I Atlas is faint. Very faint. It's not one of those spectacular comets visible to the naked eye. It requires powerful telescopes to observe it all. And to get detailed spectroscopic data, you need the best instruments humanity has ever built. Enter the telescope army. First, the James Webb Space Telescope. JWST is the most powerful infrared observatory ever constructed, positioned at a gravitationally stable point in space called L2, about 1.5 million kilometers from Earth. Its infrared capabilities are perfect for studying cold objects in the outer solar system. JWST was tasked with observing 3I Atlas in multiple infrared wavelengths, looking for the thermal signatures of different molecules. Then, there's Hubble. The venerable Hubble Space Telescope, still operational after more than 3 decades in orbit, provided sharp visual and ultraviolet observations. Hubble's role was to image the coma structure, measure its size and brightness, and look for any unusual features in the dust distribution. SphereX, a newer space-based observatory designed specifically for spectroscopy, contributed detailed spectral analysis across a wide range of wavelengths. SphereX can detect dozens of different molecular signatures simultaneously, building a comprehensive chemical profile. And then there were ground-based telescopes. Observatories in Chile, Hawaii, the Canary Islands, all coordinating observations, gathering data, contributing pieces to the puzzle. What they found was extraordinary. The spectroscopic data revealed something unexpected. 3I Atlas has an extreme carbon dioxide to water ratio, approximately 8:1. For every 1 water molecule, there are 8 carbon dioxide molecules. That is not normal. Let me give you some context. In typical comets from our solar system, the ratio is much more balanced. Water is usually the dominant volatile, with carbon dioxide present, but secondary. A ratio of 8:1 is extreme. It suggests this comet formed in a very different environment than anything in our solar system. Carbon dioxide sublimates at much lower temperatures than water ice. At the distances where 3I Atlas is currently located, carbon dioxide can easily vaporize. And that's exactly what's happening. The surface of 3I Atlas is rich in carbon dioxide ice. As the comet receives even the faint sunlight at 3 astronomical units, that CO2 begins to sublimate. As it does, it creates pressure beneath the surface. That pressure cracks the ice, breaking it apart, and ejects fragments of water ice into space. Those fragments then sublimate in the vacuum, producing the water vapor that Swift detected. So, the water production mystery is solved. It's not the water ice itself responding to sunlight. It's the carbon dioxide acting as a driver, ejecting water ice particles that then produce the observed vapor. But this raises a much bigger question. Why does 3I Atlas have such an extreme carbon dioxide ratio? What kind of place creates a comet like this? The answer lies in where it formed. The ratio of volatiles in a comet is a direct reflection of the temperature and chemical environment of its birthplace. In our solar system, comets form in the outer regions, beyond the orbit of Neptune. in areas called the Kuiper Belt and the Oort cloud. The conditions there favor a more balanced mix of water and carbon dioxide. But 3I Atlas didn't form in our solar system. It formed somewhere else. And based on that 8-to-1 ratio, it formed in a region that was colder, more carbon-rich, and chemically distinct from our own comet nurseries. Dr. Bodowitz described it perfectly in a published statement. This comet has been baked and boiled in a very different oven than our own comets. The chemical fingerprint tells us it came from a stellar system with different conditions, different chemistry, different formation history. Baked and boiled in a different oven. That's a vivid way to put it. And it's accurate. The star that 3I Atlas formed around may have been a different type of star. Different mass, different temperature, different chemical composition. The protoplanetary disk, the swirling cloud of gas and dust from which planets and comets form, would have had a different ratio of elements. More carbon, perhaps. Different temperatures at different distances. Different pressure gradients. All of that gets locked into the chemistry of the objects that form there. And 3I Atlas is carrying that chemical signature across the galaxy. Think about what that means. We're looking at a sample of material from another star system. We can analyze its composition, study its structure, understand the conditions that created it. We can't visit that star system. We don't even know which star it came from. But the star system has sent us a sample, and we can read its story in the chemistry. This is comparative planetology on a galactic scale. We're not just studying our own solar system anymore. We're studying how other solar systems form, how they differ, what kinds of environments exist around other stars, and we're doing it without leaving our own cosmic neighborhood. But the composition is only part of the story. Because when scientists calculated the age of 3I Atlas, they discovered something even more profound. Determining the age of a comet is complex. You can't just measure it directly. Instead, astronomers use a combination of techniques. One method is trajectory backtracking. By calculating the comet's current path and velocity, and accounting for gravitational interactions with the galaxy, you can work backward through time to estimate how long it's been traveling. Another method involves analyzing the comet's physical properties, the level of surface weathering, the depletion of certain volatiles, the accumulation of cosmic ray damage. All of these provide clues about how long the object has been exposed to the harsh environment of interstellar space. When these calculations were done for 3I Atlas, the result was staggering: 7 to 10 billion years old. Let me put that in perspective. Our sun is 4.6 billion years old. Earth is 4.5 billion years old. Everything you know, every rock, every mountain, every ocean, every living thing on this planet is younger than that. 3I Atlas predates our entire world by 3 billion years. 10 billion years ago, the universe itself was only 3.5 billion years old. The Milky Way galaxy was still young, still forming stars at a prodigious rate. The galaxy looked different. Stellar populations were different. The distribution of elements was different. And somewhere in that ancient galaxy, in a protoplanetary disk around a star we'll never identify, 3I Atlas formed. It formed as part of a planetary system. Maybe that system had planets. Maybe some of those planets had oceans, atmospheres, maybe even life. We'll never know. But at some point, something happened. A gravitational interaction, a close encounter with another planet, or maybe a passing star. 3I Atlas was flung out of its home system, ejected, cast into interstellar space, and it's been wandering ever since. For billions of years, 3I Atlas has been drifting through the void. The temperature of interstellar space is just a few degrees above absolute zero. In that deep freeze, the comet's volatiles are locked in place. There's no sunlight to warm it, no activity. It's essentially a frozen time capsule, preserved in the cosmic cold, unchanged for eons. Occasionally, it might pass through interstellar clouds, regions of slightly higher density where gas and dust accumulate. Cosmic rays bombard its surface, causing slow damage over millions of years. But fundamentally, the comet remains intact, frozen, waiting. And then, after billions of years of lonely travel, it happens to pass through a star system, our star system. The sun's gravity bends its trajectory slightly, but not enough to capture it. It's moving too fast. It swings through the inner solar system, passing relatively close to the sun by cosmic standards, and for a brief moment, it wakes up. The sunlight, even at 3 astronomical units, is enough to activate the carbon dioxide. The ancient ice begins to sublimate. Water vapor is released. For the first time in billions of years, this comet is active again, and we're here to witness it. There's something profoundly moving about that. We're holding, in our telescopes, an object older than our sun, older than our planet, an artifact from the ancient universe. It has traveled distances we can barely comprehend, survived timescales beyond human imagination, and arrived here, now, in this moment, when we have the technology to study it. But here's the question that haunts researchers. Why is it still so active? After 10 billion years, you'd expect much of the volatile material to be depleted. Cosmic rays should have broken down surface ices. Micrometeorite impacts should have eroded the outer layers. And yet, 3I Atlas is producing significant amounts of gas. It's behaving like a much younger comet. There are 2 possible explanations. The first is that interstellar space is an incredibly effective preservative. The cold is so extreme, the environment so stable, that the comet simply doesn't degrade the way we might expect. What looks like ancient material is, in fact, pristine, protected by the very harshness of the void. The second possibility is more nuanced. Maybe 3I Atlas is old, but its ejection from its home system was relatively recent. Maybe it orbited its star for billions of years, just like our comets orbit the sun. And then, perhaps only a few million years ago, something happened. A planetary migration. A stellar encounter. Something that destabilized its orbit and sent it into interstellar space. In this scenario, the comet itself is ancient, but its time in the interstellar void is relatively short. Both explanations have merit. Both fit the observations. And right now, we don't have enough data to definitively choose one over the other. It's one of the many mysteries 3I Atlas leaves us with. But regardless of the specifics, the fundamental truth remains. This object is a wanderer from the ancient galaxy, and it's not alone, because 3I Atlas is the 3rd interstellar object we've detected, and each one has told a different story. October 19th, 2017. The Pan-STARRS telescope in Hawaii detected a faint object moving through the inner solar system. At first, it seemed unremarkable, but as more observations came in, astronomers realized something extraordinary. This object was moving too fast to be bound to the sun. Its trajectory was hyperbolic. It had come from interstellar space. The object was named Oumuamua, a Hawaiian word meaning scout or messenger from afar. And it was bizarre. Oumuamua was unlike any comet or asteroid we'd ever seen. It appeared to be elongated, possibly cigar-shaped or pancake-shaped, with a length-to-width ratio of about 10:1. That's extreme. Most asteroids are roughly spherical or only moderately elongated. Oumuamua looked like someone had stretched a normal space rock, but the weirdness didn't stop there. As Oumuamua moved away from the sun, it accelerated. Not a lot, but measurably. Something was pushing it. With comets, this is normal. The outgassing of volatiles creates a tiny thrust, like a natural rocket engine. But Oumuamua showed no signs of a coma, no tail, no visible outgassing. It looked like an asteroid, but it was accelerating like a comet. This sparked intense debate. Some scientists proposed it was outgassing after all, just very faintly, below our detection threshold. Others suggested it could be a hydrogen iceberg, sublimating hydrogen gas that's too diffuse to see. And then there were the more speculative ideas. Could it be an alien probe? A light sail? Some kind of manufactured object? The speculation reached a fever pitch. Breakthrough. Listen, a project searching for signs of extraterrestrial intelligence pointed radio telescopes at Oumuamua. They found nothing, no signals, no transmissions, just silence. In the end, the most likely explanation is the simplest. Oumuamua is a natural object, probably rich in nitrogen ice or some other volatile that sublimates readily, producing thrust without a visible tail, but we'll never know for sure. Oumuamua passed through too quickly. By the time we realized what it was already leaving. We got a few observations, a handful of images, and more questions than answers. What we did learn is this: interstellar objects exist. They pass through our solar system, and we can detect them. Oumuamua opened the door to a new field of astronomy. 2 years later, on August 30th, 2019, Comet Borisov, an amateur astronomer in Crimea, discovered another interstellar visitor using a homemade telescope. This one was different from Oumuamua in almost every way. Comet Borisov, as it came to be known, looked like a comet. It had a coma. It had a tail. It outgassed normally. Spectroscopic observations revealed water vapor, carbon monoxide, and other typical comet volatiles. In many ways, it was reassuringly ordinary. But here's what made Borisov significant. The carbon monoxide ratio was high, higher than most comets in our solar system. Analysis suggested that Borisov formed in a colder region than our Oort cloud comets, perhaps in the outer reaches of its home planetary system, far from its parent star. Borisov gave us our first detailed look at a relatively normal interstellar comet. It showed us that not all interstellar visitors are weird like Oumuamua. Some are just comets, formed in other systems, ejected into space, wandering the galaxy. And that's important, because it tells us that planetary systems are common. Comet formation is common. The processes we see in our solar system happen elsewhere. The universe is diverse, but it follows the same physical laws everywhere. Then came 3I Atlas. Now we have 3 data points. 3 interstellar visitors. 3 completely different objects. Oumuamua, the strange accelerating enigma. Borisov, the ordinary-looking comet with high carbon monoxide. And 3I Atlas, the ancient carbon dioxide-rich water producer. The diversity is striking. Every interstellar object we've detected has been unique. And that tells us something profound. Planetary systems are wildly diverse. The conditions under which planets and comets form vary enormously from star to star. Different temperatures, different chemical compositions, different formation timelines. The variety of planetary architectures in the galaxy is staggering, and we're just beginning to sample it. Statistically, thousands of interstellar objects pass through the inner solar system every year. Maybe tens of thousands. Most of them are too small or too faint to detect. We're only catching the big ones, the ones that pass relatively close, the ones that happen to be active when we're looking. For every interstellar visitor we spot, countless others slip by unnoticed. But our detection capabilities are improving. The upcoming Vera Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky every few nights. It's designed to catch transient events, fast-moving objects, anything that changes. When Vera Rubin comes online, we expect to detect dozens of interstellar objects per year, maybe more. We're entering an era where interstellar visitor detection becomes routine. Instead of a rare, once-in-a-decade event, it'll be a regular occurrence. We'll build a library of interstellar objects, cataloging their properties, their compositions, their origins. We'll start to see patterns. We'll understand the diversity of planetary systems across the galaxy, not through speculation or theory, but through direct observation. And here's the most exciting part. Some of these objects might be carrying something crucial. The ingredients for life: water, carbon dioxide, organic molecules. These are the building blocks of life as we know it. And 3I Atlas has them. So did Borisov. These comets are delivering complex chemistry, molecules that could form the basis of biological processes across interstellar space. Dr. Bodowitz put it perfectly. The ingredients for life are not unique to our solar system. They're being transported across the galaxy. What we're seeing is material exchange on a galactic scale. Think about what that means. In our solar system, comets are thought to have delivered much of Earth's water. Impacts during the early history of our planet brought volatiles, organic compounds, the raw materials that eventually led to the emergence of life. If comets in our system did that, then comets in other systems are doing the same thing. And if interstellar comets carry these ingredients, then there's a possibility, however remote, that life's building blocks can be transported between star systems. This is the Panspermia hypothesis, the idea that life, or at least the chemistry that leads to life, can spread through space. Now, panspermia is controversial, and for good reason. The interstellar environment is harsh. Cosmic rays, ultraviolet radiation, extreme cold. Can organic molecules survive that? Can they remain intact over millions or billions of years of travel? Laboratory experiments suggest that some can. Certain organic molecules are remarkably resilient. When frozen in ice and shielded from direct radiation, they can survive for extended periods. Amino acids, the building blocks of proteins, have been found in meteorites. Complex hydrocarbons exist in interstellar space. The chemistry of life is hardy. But whether that chemistry can actually seed life on another world is still an open question. The conditions have to be right. The molecules have to arrive intact. The target planet has to be habitable. The odds are long, but the galaxy is vast. Billions of stars, trillions of planets, countless comets ejected into the void. Over billions of years, even unlikely events become probable. 3I Atlas is a data point in this grand experiment. It's carrying water, carbon dioxide, likely organic molecules. It formed in another star system, perhaps in the same kind of protoplanetary disk where planets were forming. Maybe some of those planets have life now. We'll never know. But the comet is here, and we can study it. The connection to exoplanet research is direct. We've discovered thousands of exoplanets in recent years. Planets orbiting other stars. Some are gas giants. Some are rocky worlds. Some orbit in the habitable zone, where liquid water could exist on the surface. We study these planets from afar, analyzing their atmospheres, looking for signs of water, oxygen, methane, the gases that might indicate life. But we can't visit them. The distances are too great. Even the nearest exoplanets are light years away. With our current technology, a journey to even the closest star system would take tens of thousands of years. But the universe is bringing samples to us. Interstellar objects like 3I Atlas are fragments from exoplanet systems. They formed in the same environments where those distant worlds are forming. By studying these visitors, we're doing exoplanet science without leaving our solar system. We're analyzing the construction zones of alien worlds. Every interstellar comet is a gift, a piece of another star system delivered across the void, arriving at our doorstep just when we have the technology to study it. The timing is remarkable. 100 years ago, we wouldn't have known what 3I Atlas was. We might not have even detected it. But now, in this moment, we can capture it with our telescopes, analyze its spectrum, decode its chemistry, and learn its story. And that required an extraordinary global effort. Observing an interstellar object is not easy. These things are faint, fast-moving, and fleeting. 3I Atlas was detected when it was already relatively close to the Sun, which means the window for detailed study was limited. From the moment of discovery, astronomers knew they had only a few months to gather as much data as possible before the comet faded from view. The challenge is immense. 3I Atlas is small, distant, and not particularly bright. Even at its most active, it was barely visible to professional telescopes. To get spectroscopic data, to analyze its composition, to measure its water production, required some of the most powerful instruments on and off Earth, and it required coordination. Global coordination. Within days of the initial detection, the astronomical community mobilized. Alert systems notified observatories around the world. Telescope time, normally allocated months in advance, was reshuffled to accommodate urgent observations of the interstellar visitor. This is not a simple process. Major telescopes have waiting lists. Researchers compete for time. Every hour is precious. But when an interstellar object appears, priorities shift. Ground-based observatories in Chile moved first. The Chilean telescopes have some of the clearest skies on Earth. The Atacama Desert, at high altitude, with minimal light pollution and dry air, provides ideal conditions for astronomical observation. Large instruments like the Very Large Telescope and the Magellan telescopes turn their mirrors toward 3I Atlas, capturing spectra, measuring brightness, tracking its motion. In Hawaii, observatories on Mauna Kea joined the effort. Mauna Kea is one of the best observing sites in the world, nearly 14,000 feet above sea level, above much of the Earth's atmosphere. The twin Keck telescopes, each with 10-meter mirrors, provided high-resolution spectroscopy. The Canary Islands contributed observations from the Gran Telescopio Canarias, one of the largest single-mirror telescopes on the planet. South Africa's Southern African Large Telescope added data from the Southern Hemisphere. This was a coordinated campaign. Dozens of observatories, hundreds of astronomers, all focused on one target. Data flowed in from around the globe, building a comprehensive picture of 3I Atlas. But ground-based telescopes have limitations. The Earth's atmosphere absorbs certain wavelengths of light, particularly in the ultraviolet and infrared. To get the full spectrum, you need space-based observatories. That's where the James Webb Space Telescope came in. JWST, positioned far beyond Earth's orbit at the L2 Lagrange point, observed 3I Atlas in infrared wavelengths. Infrared is critical for studying cold objects. The thermal emission from ice and dust is strongest in the infrared. JWST's instruments are incredibly sensitive, capable of detecting faint signals that would be invisible to other telescopes. JWST observed 3I Atlas for multiple sessions, building up exposure time, gathering photons, extracting spectral data. The observations revealed the thermal properties of the coma, the temperature distribution, the composition of the gases being released. This is data you simply can't get from the ground. Hubble Space Telescope added its own observations. Hubble, though older than JWST, has unparalleled sharpness in visible and ultraviolet light. Hubble imaged the structure of the coma, revealing details about how gas and dust are distributed around the nucleus. These images showed asymmetries in the coma, suggesting that the nucleus is rotating, that jets of gas are being released from specific active areas on the surface. The Neil Gehrels Swift Observatory, as mentioned earlier, detected the hydroxyl signature with its ultraviolet detectors. Swift was designed to catch gamma-ray bursts, sudden explosions of high-energy radiation from distant galaxies. But its instruments are versatile. The ultraviolet telescope on Swift is perfect for detecting the byproducts of water vapor. When Swift observed 3I Atlas, it confirmed that water production was ongoing and quantified the rate, 40 kilograms per second. SphereX, a space telescope designed for all-sky spectroscopy, provided broad spectral coverage. SphereX can observe across a wide range of wavelengths simultaneously, creating a detailed chemical fingerprint. Its observations of 3I Atlas contributed to the identification of the carbon dioxide to water ratio. Each telescope contributed a piece of the puzzle. Infrared data from JWST, ultraviolet data from SWIFT and Hubble, visible light spectra from ground-based observatories, all of it combined to create a comprehensive understanding of this ancient visitor. But here's where it gets truly remarkable, because the most challenging observations came from an unexpected source: Mars. Two spacecraft currently orbiting Mars, the European Space Agency's Mars Express and the ESA Roscosmos Trace Gas Orbiter, are designed to study the Martian atmosphere and surface. They're not built for observing distant comets. Their cameras and instruments are optimized for close-range imaging of a nearby planet, not faint objects millions of kilometers away. But someone had an idea. What if we could use these Mars orbiters to observe 3I Atlas? From Mars's perspective, the comet would be at a different angle, providing a unique vantage point. Stereoscopic observations from Earth and Mars could help determine the three-dimensional structure of the coma, refine estimates of the nucleus size, and provide additional data points for understanding its activity. The technical challenge was enormous. From Mars, 3I Atlas would be incredibly faint. The cameras on Mars Express and Trace Gas Orbiter are sensitive, but they're designed to photograph a bright planet from close range, not a dim comet from millions of kilometers. The brightness difference was staggering. 3I Atlas would be 10,000 to 100,000 times fainter than the typical targets these instruments image. To make the observation work, engineers had to calculate the precise pointing required, accounting for the motion of the comet, the motion of Mars, the motion of the spacecraft. They had to maximize exposure time without smearing the image due to motion. They had to push the cameras to their absolute limits, and they succeeded. In October 2025, both Mars Express and Trace Gas Orbiter captured images of 3I Atlas. The images were faint, very faint. In some cases, the comet was barely a few pixels, a dim smudge against the background stars. But it was there. The detection was confirmed. Dr. Nick Thomas, a planetary scientist involved in the Mars orbiter observations, said, "This was pushing the boundaries of what these instruments were designed to do. We weren't sure it would work, but the fact that we pulled it off, that we captured an interstellar comet from Mars orbit, is a testament to what we can achieve when we push our technology to its limits." The successful imaging from Mars was more than just a technical achievement. It was symbolic. We have spacecraft at another planet, and we're using them to observe visitors from other star systems. We're conducting astronomy from multiple worlds simultaneously. That's a level of capability that would have seemed like pure science fiction just a few decades ago. And it worked because of data synthesis. All of these observations, from Earth, from space, from Mars, were combined. The infrared data from JWST was cross-referenced with the ultraviolet data from SWIFT. The ground-based spectra were compared with the space-based measurements. The images from Mars provided additional constraints on the size and shape of the coma. This is modern astronomy. No single telescope can do it all. It takes a network, a global, coordinated effort, leveraging the strengths of different instruments, different wavelengths, different perspectives. And when it works, when all of that data comes together, you get something extraordinary. A comprehensive portrait of an object from another star system. We caught 3I Atlas. We studied it. We decoded its chemistry. We measured its age. We witnessed its activity. And we did it all in a matter of months during the brief window when the comet was bright enough to observe. But there's a bittersweet reality to all of this. We can observe 3I Atlas. We can analyze its light, but we can't touch it. We can't collect a sample. We can't send a spacecraft to intercept it. Or can we? Imagine this. A spacecraft intercepts 3I Atlas. It matches velocity, flies alongside the comet, deploys instruments to study it up close. Cameras capture high-resolution images of the nucleus. Spectrometers analyze the coma in exquisite detail. A sample collection arm extends, touches the surface, scoops up material. The spacecraft then returns to Earth, carrying physical samples from another star system. It's a beautiful dream. And it's technically possible. Sort of. Let's talk about the engineering reality. 3I Atlas is currently traveling at approximately 210,000 kilometers per hour relative to the Sun. That's about 58 kilometers per second. To intercept it, a spacecraft would need to match that velocity. Not just reach the comet, but actually catch up to it and travel alongside it. For comparison, New Horizons, the spacecraft that flew past Pluto, is one of the fastest human-made objects ever launched. It left Earth at a speed of about 58,000 kilometers per hour. That's fast, but it's less than a third of the speed of 3I Atlas. The challenge is something called delta V. Delta V is the change in velocity required for a maneuver. To intercept 3I Atlas, you need enough delta V to accelerate from Earth's orbital velocity to the comet's velocity. That's a massive energy requirement. Chemical rockets, the kind we currently use for most space missions, simply can't do it. The amount of fuel required would be prohibitive. You'd need a rocket larger than anything we've ever built, and even then, you'd struggle to carry enough propellant to reach the necessary speed. Ion drives are more efficient, but they're slow to accelerate. An ion drive produces a small, continuous thrust over a long period. This works great for missions to asteroids or outer planets, where you have years to accelerate. But 3I Atlas is already here, already moving through the solar system. We don't have years. We have months, maybe a year or two at most, before it's too far away to reasonably intercept. Nuclear propulsion is a possibility. A nuclear thermal rocket, which heats propellant using a nuclear reactor, can achieve higher exhaust velocities than chemical rockets. This would provide more delta V for the same amount of fuel. But nuclear rockets are controversial, politically complicated, and not currently operational. Developing and launching such a system would take years, possibly decades. There's also the breakthrough starshot concept, a light sail pushed by powerful ground-based lasers. This could theoretically accelerate a tiny probe to a significant fraction of light speed. But the technology is still in the conceptual phase. We're talking about postage stamp-sized spacecraft, not something capable of sample return. Even if we had the propulsion technology, there's the issue of time. 3I Atlas was discovered in July 2025. By the time scientists characterized it, confirmed it was interstellar, and realized its significance, it was already October. To design, build, and launch a mission takes years. NASA's New Horizons took 5 years from approval to launch, and that was for a relatively straightforward flyby mission to a known target. An intercept mission to an interstellar object would be far more complex. You'd need to design instruments specifically for the science goals. You'd need to develop the propulsion system. You'd need to plan the trajectory, accounting for the comet's motion and the launch windows. And if you wanted sample return, you'd need to figure out how to bring material back to Earth, which adds another layer of complexity. Realistically, by the time a mission could be ready, 3I Atlas would be long gone. It's a harsh reality. We detected it too late. We weren't prepared. And our current technology, while impressive, isn't fast enough. But let's imagine we did it. Let's imagine we somehow managed to intercept 3I Atlas and return samples to Earth. What could we learn? First, isotopic analysis. The ratio of different isotopes in the comet's ice and rock would tell us about the conditions in the protoplanetary disk where it formed. Isotopes are like fingerprints. Different environments produce different isotopic signatures. By measuring the ratios of oxygen isotopes, carbon isotopes, nitrogen isotopes, we could reconstruct the temperature, pressure, and chemical composition of the disk. Second, Organic molecule identification. Spectroscopy can detect molecules in the gas phase, but physical samples allow for much more detailed analysis. We could use mass spectrometry to identify complex organic compounds, amino acids, maybe even prebiotic molecules. We could study how these molecules are preserved in ice over billions of years. Third, mineral dating. By analyzing the crystalline structure of minerals in the nucleus, we could refine the age estimate. Radioactive decay of certain isotopes provides a clock. The more precisely we can measure that decay, the more accurately we can determine when the comet formed. Fourth, comparison to solar system materials. We have samples from asteroids, samples from comets, and meteorites that have fallen to Earth. We can compare the composition of 3I Atlas to these known samples and see how it differs. This would give us direct evidence of how planetary systems around other stars differ from our own. And fifth, the possibility of preserved ancient life signatures. This is speculative, but not impossible. If the star system where 3I Atlas formed had planets with life, and if material from those planets was somehow incorporated into the comet, there could be biosignatures, fossilized microbes, organic molecules with specific chirality, chemical patterns that suggest biological processes. The chances are astronomically slim, but the payoff would be profound. All of that is locked inside 3I Atlas, and we can't reach it. But here's the hopeful part. We're learning from this. The astronomical community is acutely aware that interstellar visitors appear without warning and disappear just as quickly. The time to study them is limited, and if we want to do more than just observe, if we want to actually visit these objects, we need to be ready in advance. Enter the concept of rapid response missions. The idea is simple. Have a spacecraft pre-built, sitting in storage or even in orbit, ready to launch on short notice when an interstellar object is detected. The spacecraft would be equipped with a versatile suite of instruments, capable of adapting to whatever target appears. The propulsion system would be designed for maximum delta V, optimized for intercept trajectories. The European Space Agency is already working on this. It's called Comet Interceptor. The mission is scheduled to launch in the late 2020s and will wait at a gravitationally stable point in space, monitoring for new comets or interstellar visitors. When a suitable target is detected, Comet Interceptor will leave its holding position and fly to intercept it. Comet Interceptor isn't specifically designed for interstellar objects, but it could be retargeted if one appears. The spacecraft consists of 3 separate probes that will approach the target from different angles, providing multi-point observations. It's designed to study pristine comets, objects that have never passed close to the Sun before, but the same technology applies to interstellar visitors. NASA and other space agencies are studying similar concepts. The idea of having a pre-positioned spacecraft ready to respond is gaining traction. It's a paradigm shift. Instead of designing a mission after a target is discovered, you design the mission in advance and wait for the target to appear. This approach has challenges. You don't know what kind of object will show up. It could be icy like 3I Atlas, rocky like Oumuamua, or something entirely unexpected. Your instruments need to be versatile enough to handle any scenario. Your propulsion system needs to be powerful enough to reach a wide range of possible trajectories. And you need to be patient. You might wait years for the right target. But the potential payoff is enormous. Imagine capturing detailed images of an interstellar object's nucleus. Imagine measuring the isotopic composition in situ. Imagine, perhaps, even returning a sample. For 3I Atlas, it's too late. We missed the window. But the next interstellar visitor? We might be ready. Statistically, we won't have to wait long. With improved detection capabilities, we're finding these objects more frequently. Oumuamua in 2017, Borisov in 2019, 3I Atlas in 2025. The intervals are getting shorter, As survey telescopes like Vera Rubin come online, we expect to detect multiple interstellar objects per year. One of them will be the right target. Close enough, slow enough, detected early enough, and when that happens, we'll have a spacecraft ready to go. That's the future we're building toward. A future where interstellar visitors aren't just observed from afar, but studied up close, where we can touch samples from other star systems, analyze them in laboratories, hold fragments of alien worlds in our hands. We're not there yet, but we're getting closer. In the meantime, we have 3i Atlas. We can't touch it, but we can learn from it. And what we've learned is reshaping our understanding of the cosmos. Let's take a step back and look at what 3i Atlas has taught us. Because in the brief months we've been able to observe it, this ancient wanderer has delivered insights that will occupy researchers for years to come. First, detection capabilities. We can now reliably spot and characterize interstellar visitors. The global network of telescopes, the alert systems, the rapid response protocols, they all worked. When 3i Atlas appeared, astronomers recognized it quickly, mobilized resources efficiently, and gathered comprehensive data. A decade ago, we might have missed it entirely, or dismissed it as just another faint comet. Today, we have the infrastructure to catch these objects and the expertise to study them. That's progress. But we also know what we need to improve. Earlier detection would be ideal. If we could spot interstellar objects farther out, when they're still beyond Neptune's orbit, we'd have more time to observe them, more opportunity to plan missions. Upgraded survey systems are coming. Vera Rubin Observatory will help. But there's room for improvement in automated recognition algorithms, in real-time trajectory calculations, in global data sharing. Second, the water production mystery. 3i Atlas showed us that comets can be active in ways we didn't fully understand. Water vapor at 3 astronomical units, driven by carbon dioxide sublimation, ice grain ejection mechanisms. This is new physics, or rather, it's physics we knew existed but hadn't observed so dramatically. The mechanism is now clear. Subsurface carbon dioxide creates pressure, fractures the ice, ejects fragments, and those fragments release water vapor. But questions remain. How common is this process? Do comets in our solar system do the same thing, and we just haven't noticed? What does this tell us about activity on distant comets that we can't observe in detail? Researchers are building new models, refining simulations, trying to predict when and where we'll see this kind of activity again. The implications extend beyond 3i Atlas. Understanding how comets activate at large distances helps us interpret observations of comets in other star systems, once we have the capability to detect them. Third, composition insights. That 8:1 carbon dioxide to water ratio is a window into the chemistry of another star system. It tells us about the protoplanetary disk where 3i Atlas formed. Colder conditions, carbon-rich environment, different volatile distributions. This is direct evidence of planetary system diversity. Every star system is unique. The conditions that created 3i Atlas are different from the conditions that created our comets. That difference is measurable, quantifiable, and it gives us a framework for understanding how planetary systems vary across the galaxy. When we compare 3i Atlas to Borisov, and both to our solar system comets, patterns emerge. We're starting to build a taxonomy of comets based on their origin environments. Carbon-rich systems, water-rich systems, different formation temperatures, different chemical pathways. This is comparative planetology in action, and it's only possible because interstellar visitors bring samples to us. Fourth, age implications. 7 to 10 billion years. That number is staggering. Material older than our sun exists, and we can study it. Not just theoretically, not just by looking at distant galaxies and inferring what ancient stars were like. We have an actual object from the early galaxy passing through our solar system, close enough to observe in detail. The preservation of this comet over such vast timescales tells us something profound about interstellar space. It's cold, it's stable, it's a natural cryogenic storage facility. Objects can survive essentially unchanged for billions of years if they're flung into the void. This has implications for everything from our understanding of the early solar system to the possibility of panspermia. If material can survive that long, then yes, chemistry can be transported across enormous distances and timescales. The galaxy has memory. The past is not lost. It's drifting through space, waiting to be discovered. Fifth, planetary system diversity. We've now studied 3 interstellar objects, and all 3 are different. Wildly different. That tells us the galaxy is full of variety. Not every star system looks like ours. Not every planetary formation process follows the same path. There are carbon-rich systems, nitrogen-rich systems, water-rich systems. There are systems with close-in giant planets that disrupt comet formation. There are systems with distant stellar companions that gravitationally stir the outer regions. Every variable in the planet formation equation can change, and the result is a galaxy of unique outcomes. This diversity is exciting because it expands the possibilities for where and how life might emerge. If planetary systems are this varied in their chemistry and structure, then the range of potentially habitable environments is broader than we might have assumed. Sixth, astrobiology implications. Life's ingredients are common: water, carbon dioxide, organic molecules. They're not unique to our solar system. They're being created in protoplanetary disks around other stars, incorporated into comets and asteroids, and distributed across the galaxy. Some of that material ends up on planets. Some of it might seed prebiotic chemistry. We don't know if life exists elsewhere, but we know the raw materials are there. The building blocks are universal. Doctor. Bodwitz was right. The ingredients for life are not unique to our system, and that's a hopeful message. It suggests that whatever chemical pathway led to life on Earth, it could happen elsewhere. The galaxy is full of potential. Right now, papers are being published. Scientists are analyzing the data, refining models, debating interpretations. Graduate students are writing dissertations on 3I Atlas. Textbooks will be updated to include this discovery. In classrooms around the world, teachers will tell the story of the ancient comet that visited our solar system in 2025. This is how science advances, one observation at a time, one insight building on another. 3I Atlas is a single data point, but it's a significant one. And it's part of a growing body of knowledge about interstellar objects, about planetary systems, about the nature of the galaxy we live in. There are still unanswered questions. We don't know exactly which star system 3I Atlas came from. We can backtrack its trajectory to some extent, but the uncertainties grow over time. After billions of years of wandering, pinpointing its origin is nearly impossible. We don't know if its home system still exists. Stars die. Planetary systems are disrupted. It's entirely possible that the star that 3I Atlas formed around is gone, long since exhausted its fuel and collapsed into a white dwarf or exploded as a supernova. The comet might be the last remnant of a system that no longer exists. That's a sobering thought, but it's also a reminder of the impermanence of everything. Stars are born. Stars die. Planets form. Planets are destroyed. And through it all, some objects endure, carrying with them the memory of what once was. 3I Atlas is still out there. Right now, as you're hearing these words, it's moving away from the sun, heading back into the darkness. Its activity is declining. The carbon dioxide is depleting. The water production is dropping. Soon, it will become too faint to observe. Within a few years, it will fade from our telescopes entirely, slipping back into the void from which it came. We will never see it again. Its trajectory is taking it out of the solar system, never to return. In the grand scheme of cosmic time, its visit was a blink. A brief moment when an ancient traveler happened to pass through our neighborhood, and we happened to be watching. But brief doesn't mean insignificant. Think about the journey of humanity. For most of our history, we looked at comets and saw omens, portents of disaster, messengers from gods. We didn't understand what they were. We didn't know where they came from. We could only watch and wonder. Then came the scientific revolution. We learned that comets are natural objects, icy bodies orbiting the sun. We calculated their orbits. We predicted their returns. We sent spacecraft to fly past them, to orbit them, to land on them. We transformed comets from mysteries into subjects of study. And now, in 2025, we're analyzing visitors from other star systems. We're studying material that formed around alien suns. We're doing comparative planetology across light years. We're using telescopes on Earth, in space, and on other planets to observe objects from the ancient galaxy. That's an extraordinary progression, from fear and superstition to scientific understanding in just a few centuries. And we're not stopping. We're building better instruments. We're planning intercept missions. We're preparing for a future where interstellar visitor study is routine. We're becoming a species that thinks on galactic scales, not just about our planet, not even just about our solar system. We're thinking about the galaxy as a whole, about how matter flows between stars, about how planetary systems form and evolve across billions of years, about our place in a cosmos vastly larger and older than ourselves. 3I Atlas is a teacher. It's showing us what's possible. It's demonstrating that the universe is interconnected. Stars are not isolated. Planetary systems are not closed loops. Material moves between them. Comets are ejected. They wander. They visit other systems. And occasionally, one visits us. Right now, in this moment in October 2025, we're living through something historic. 3I Atlas is here. We're observing it. We're learning from it. This is happening during our lifetimes. We're the generation that gets to witness this. And that's remarkable. Think about what your grandchildren will know. They'll grow up in a world where interstellar objects are detected regularly, where missions to intercept them are launched routinely, where samples from other star systems are analyzed in laboratories, where the diversity of planetary formation across the galaxy is common knowledge. They'll look back at this era, at the 2020s, as the time when it all began. When Oumuamua first announced that interstellar visitors exist. When Borisov showed they can be ordinary. When 3I Atlas revealed they can be ancient and exotic. We almost missed it. If the Atlas telescope hadn't been scanning that particular patch of sky on that particular night, if the object had been slightly fainter or slightly farther away, if astronomers hadn't recognized the significance quickly enough, we might never have known 3I Atlas was here. But we didn't miss it. We caught it. We studied it. We learned from it. And that happened because of infrastructure, because of decades of investment in telescopes, in survey systems, in international cooperation, because scientists built networks, shared data, coordinated observations, because engineers designed instruments that can push the boundaries of detection, because institutions prioritized this kind of research. Science is a collective endeavor. It's not one person making a discovery. It's thousands of people contributing over years, building on each other's work, creating the foundation that makes discoveries possible. 3I Atlas was discovered because generations of astronomers built the tools, developed the techniques, and trained the next generation to use them. That's worth celebrating. We're capable of remarkable things when we work together, and we're just beginning. The next interstellar visitor is already on its way. It might arrive next year. It might arrive in a decade. But it's coming, and when it does, we'll be ready. We'll point our telescopes toward it. We'll analyze its light. We'll decode its chemistry. We'll add it to our growing catalog of cosmic visitors. And with each one, we'll learn a little more about the galaxy we inhabit. 3I Atlas is leaving. Its brief moment in our skies is ending. But the knowledge it's given us will endure. The data will be analyzed for years. The insights will inform future research. The inspiration will spark new questions, new missions, new discoveries. This is what exploration looks like in the modern age. We don't need to travel to other star systems to study them. The universe is bringing samples to us. Ancient travelers, wandering the galaxy, occasionally passing through our neighborhood. And all we have to do is watch, listen, learn. Where is 3I Atlas now? It's several astronomical units from the Sun, moving outward, fading. In a few years, it will cross the orbit of Neptune. In a few decades, it will be beyond the Kuiper Belt. In a century, it will be farther from the Sun than any spacecraft we've ever launched. And it will keep going, back into the void, back into the darkness between stars. Its journey continues. The journey that began billions of years ago in a star system we'll never know, around a sun that may no longer exist. A journey through the galaxy, through clouds of gas and dust, past countless stars, across distances that dwarf anything we can truly comprehend. And for a brief moment, that journey intersected with ours. We were here to witness it. We had the technology to study it. We had the curiosity to understand it. And we did. That's something to be proud of. That's something to build on. The universe is vast. The galaxy is ancient. And we're part of it. Not separate observers watching from afar, but participants in a cosmic story that spans billions of years. We're made of material forged in stars. We live on a planet shaped by impacts from comets and asteroids. We're connected to the galaxy in ways both physical and profound. 3I Atlas is a reminder of that connection. A piece of the ancient universe, passing through, leaving us with knowledge and wonder. Keep watching the skies. The next visitor is coming, and who knows what secrets it will bring. The cosmos is full of mysteries, and we're learning to read them, one ancient comet at a time.